I did this sort of as a joint trip. I went to Monetic Warsaw and gave a talk in Poland, and then I came here. I was thinking about doing the same talk for both venues, and Gleb was constantly pestering me for my talk title for the last 3 months. And I finally told him yesterday, or the day before. Because I didn't really want to do the same talk as I used in Poland. And at the end of the talk I gave there, I said, okay, we built up all this stuff for the last hour and a half, and here's all the problems with it. Maybe I could get away with something simpler. So now I'm going to try and get away with something simpler. And you won't have to burden yourself with what was in the other talk. So here's the sort of problem that I want to address. We have all this work going on with effect systems, and we have the MTL lying around and what have you. I'm not going to get into effects versus MTL today. But what I do want to get into is that the way that we use the MTL is in many ways suboptimal, or the way that we use monad transformers is somewhat suboptimal in terms of the code that we get generated. So what do we teach everyone to do when they go to write MTL code? Switching to the, yeah, it went to sleep on me here. Screen should be connected. This button. Content shared. All right. Woo. Let me make this thing big enough. So, is that a reasonable scale for people to be able to see? All right, good. We teach people to write something like, I have my combinator foo, and it's going to take a monad writer, EM, and a monad state, SM, and if we're really lensy, we might have has foo and all this kind of stuff, and then we generate like an M event, and I run out of screen space. So this is the style that we teach people to work with the MTL, because they write their functions parametric in the choice of monad, just so long as it's any monad that has access to a state and has access to the ability to scribble out to a monoid, whatever E was, then this will work, so they can add new layers to the monad transformer, and this will still work in the larger environment, right? And the sort of has foo, has bar kind of constraints that people who like to use lens use can then build up the big product environment, or the big product state. Okay. The problem that this approach has is, what does GHC do when it encounters one of these things? Like if you wrote this perfectly generic definition for my particular, or for this, completely abstracted out monad, how does it compile a small function that's written this way? Well, what it's going to do is it's going to have to look up through monad writer, look up the superclass of it, find that's monad, go into the monad, figure out how return and bind work, pull out how get and tell and put work by looking through these dictionaries, right? And since this is written to sort of an abstract M, every step is, whether may I, how do I go get return? Okay, all right, and I'm going to bind the result of that to get, okay, and how do I bind the result of that? I'm F mapping here. Each one of these things is constantly doing dictionary lookups. So we go, well, the inliner will solve that, right? And it won't be a problem anymore. It'll get specialized away based on the inlining this code. But the moment this stuff is a recursive function, the inliner really kind of gives up. So if we're teaching people to write in this very abstract style, what we're teaching them to do is to write really bad code from an efficiency standpoint. And even the core implementations of all the monad and stuff like that for the various transformers, up until this very last release that I got Ross to push out, where we finally added all the inline pragmas in the appropriate places. Like the MTL wasn't inlining very well, just even when you're working with a concrete stack. But now if you're working with a concrete monad transformer stack, it can be quite efficient. So what I'm interested in is there a better way, at least potentially, from a performance standpoint, to write monadic code, okay? And still have sort of power and flexibility of the MTL. And when I was playing with this before, I used the first stab that I took at this, the very thing that I said that I wasn't going to drag in this talk, was to play with lenses in different categories. So it turns out that lenses can live, you can build lenses on any category that has a monoidal category. And last year, I gave a talk here and I introduced monoidal categories, and then I went through and built up like contrariant forms of applicative and then used it to build discrimination and all that stuff. But if you remember the definition of a monoidal category from last year, I'll just assume everyone here does. You can then show that the category of monad transformers, if you drop a couple of pesky monads, forms a monoidal category in its own right, and you can do all sorts of crazy things there. That wasn't good enough to get the behavior I wanted. So at the end of that talk, I sat down and I said, well, maybe I can just get away with building a library for manipulating sort of monad homomorphisms. So let's talk about what a monad homomorphism is. We can get some basic vocabulary for how to wire these things up, because my goal is to be able to say, I have a big monad that I want to run my computation in ultimately. I have a small monad that has just the features that I need for this particular thing that I want to do. I want a monad homomorphism that embeds this computation in this larger context by swizzling out the parts of the environment or the state or the result type or whatever that we're going to, that we need, feeding it into this computation, and then pulling the results back and swizzling them back into place in the larger monad that I want to run in. Okay? And so in order to make that make sense, we need to have the definition of what a monad homomorphism is. In order to be able to reason about them, I'd like to talk about some vocabulary that comes out of the category theory world about monic and epic and isomorphisms and stuff like that. And then we can start seeing what monad homomorphisms I have, which ones of them satisfy these quantities or these properties, and we can go from there. Does that seem like a reasonable direction for this to go? Okay, so let me pull up. Oh, I lost the screen again. Start sharing. Yes. All right. So I banged out this yesterday and the day before, and this makes a nice sort of way to precurse or to keep people from getting too distracted by what's coming ahead. They can't see anything yet. Okay, so yes, we keep going past imports. So we have a bunch of existing monad homomorphisms that we know. Lift from monad trans is a monad homomorphism. It says that if M is a monad, then T of M is a monad. Well, we really want T of M to be a monad. Monad trans isn't smart enough to tell us that. We're missing something. What's going on? Well, what I want is we have class monad trans, T. We have lift says M of A goes to TMA, right? And this is for any monad M. And this has some laws. Lift of return A is return A. And lift of M bound to some function F is lift M bound to lift.F. Right? We can state the laws that lift distributes over this. It's a monad structure preserving natural transformation. So a natural transformation takes, some functor F to a functor G. It maps F of A to G of A for all A in a natural way, which means that if you were to F map before you apply the natural transformation or F map after you apply the natural transformation, you'll get the same answer. So if you F map then transform or transform then F map, you'll get the same answer. This is the same thing, but now so you can think of a natural transformation as a functor preserving map. This is a monad homomorphism that is a monad preserving map. It's that plus the extra laws about return and bind. So this is the definition that we all know and love, but there's a problem. If you actually start using this in anger, and there actually was a library that attempted to do this. There's an mmorph library. And at the last minute this morning, I changed all my vocabulary to match the mmorph library's combinator names. So I may get things totally wrong. The problem is that there's a missing concept here that makes it so that library has to jump through some hoops. And that is that monad trans is missing something that it should be able to state. It should state one more thing, which is not just that there is a monad homomorphism from M to T of M, but that T of M is a monad if M is a monad. Right? I want something that proves to me that if I know that M is a monad, then T of M is a monad. Now this funny symbol here is something we can define by building a little library. And I built it on Hackage. It's called constraints. But to sort of unpack that for people who are really Haskell savvy and want to, this is P and tails, dict Q, there. So in 7.4, Max Bolingbroke gave us the ability to abstract over constraints, the stuff that goes on the left-hand side of a double arrow. Before, we used to be able to define something like data ord dict A, where ord dict was given ord of A, I'll give you ord dict for A. But you'd have to do this point-wise for every individual class you wanted to deal with. Now, we can abstract over things of kind constraint. So there's a kind constraint such that if you look at ord has kind star to constraint, and monad has kind star to star to constraint. So here we can say dict has type dict of, I don't know, ord int. Go capture the ordering on ints into this thing. And so if I open it up in a later context, I can work with it. And another example would be using the thing that I wrote just below this. I can say, go prove to me GHC. You know, I can say like foo equals subdict, such that GHC, please do all the work to show me that if I know ord of A, then eq of list of A is there, right? And GHC will compile that and just say yes. And that thing will be the proof that given a dictionary for ord of A, we can walk up to the superclass getting ord of eq A, and we can use the instance eq A entails eq of list of A many times to get to that particular concrete thing. So GHC will just do that. That's what I said here. Subdict. Sub, which creates a context that demands, in this case, an ord A, and then tries to figure out how to build this other dictionary for us. So this stuff is all nicely packaged up. Well, maybe not nicely, but I'm packaged it up. And in that package, let me actually keep this thing because now I'm at least self-contained. There is another ridiculously generic class I have called lifting. And lifting PF has one operation, which is that if I have P of A, then P of F of A. Okay? That looks suspiciously like transform. Let's swap in monad for P and M for A and T for F. I should have chosen my letters better. Right? And if we do that, then transform is just a special case of this. So we're looking for a lifting monad instance for my particular monad transformer. That's the piece that is missing from monad trans. What is so what I want to do is this. I want to think a little bit about the category of monad homomorphisms, or the category of monads over Haskell data types. Okay? So there's so we have the category of Haskell data types where we have functions as our arrows, and we can compose them. We have the identity function, and that has all sorts of rich structure. We can look at the category of monads over Haskell, and that also has interesting structure. So the arrows in the category of monads will be monad homomorphisms from one monad to another. So they're going to like preserve at least the structure of return and bind and fmap and the things that are above monad. And then what is monad trans in terms of that category, right? This is morally equivalent to the pointed class, which I don't particularly like in the Haskell ecosystem. It's that it's return. Right? If you squint at this, if you kind of look at, if you get rid of the A's, right? This is A goes to M of A, or M goes to T of M, right? It's morally return, but without fmap. We don't have an fmap. What's going on? This isn't even a pointed functor. So we can try and make this a little bit cleaner looking by making a little type alias. It says for all A, M of A goes to N of A, and I'll imply that this will always be a monad homomorphism when I write these, just because That's the domain of discourse today. So now we can write it that way, and now it looks a little closer. So let's go build up a notion of like a monad functor. Well, what do we want? We want some operation. I'm going to use the name that I used originally that I think Gabriel stole for mmorph later on, which says that if you give me a monad homomorphism from M to N, I'll give you a monad homomorphism from Tm to Tn. Darn it, that feels very functory. And this has to be for all for monad M and monad N. Right? That's a functor on the category of monads of monads over Haskell. The thing that's missing here is that we really need to know that this lifts monad, lifting monad T, and that says that you can play games to open up this dictionary whenever you really need to prove that T of M is a monad. Because like if you were to nest monad transformers, S of T of M, you're going to otherwise wind up with all these annoying constraints that monad has to be a monad, or M has to be a monad, but T of M also has to be a monad, and then we can say that S, then you can lift into S. You've probably, if you've beat on MTL in anger, sometimes you'll get these annoying, I need the monad for T of, oh God, this lets me work around it by doing horrible cases in places that I don't want to do, but it was a missing thought. So we can call this like M pointed down here, which will be lifting monad T and monad trans T will be the sort of equivalent of the pointed functor class. We'll just say, hey, there's an instance. So this is, now, if you're familiar with the type aliases, then we have the fact that we have this constraint kind, you might be wondering why I didn't bother to write like type M pointed. Didn't go to sleep on me again, good. Is this, right? They seem equivalent, except for the fact that this type alias can't be partially applied. I can't talk about M pointed without applying it to an argument. If it's a type alias, this thing here, I can apply to an argument. So even though I can make type aliases for constraints, I almost never can get away with actually using it. Side tangent. So we have pointed, we have functor. We can also build monads in the category of monads. What would be an M monad, right? Well, we should be M pointed. We should be an M functor. We have some sort of mu-like operation here, let's call it. Our squash, I think, was the, I'm paging in the M-morph vocabulary. Squash is, I think, what they called it there. This would be like T of M, T of M. So what is this? This is something like, if I have two levels of reader T for the same environment, I can mash it down and get a reader T. Okay. Using the bind form of it's perhaps a little more useful. But now we've got something that sort of feels familiar. If you think about it, monad trans, the thing that we've always had, is almost pointed. So we can think of monad transformers as almost being pointed functors on the category of monads. The problem is that they didn't have an F-map. And then if we say, well, we can always equip it with an F-map, we're wrong because Kant doesn't let you do that. So there are certain things that, like, Kant is like the moral equivalent of like set. You know, you can't make the functor instance of it, but it's pointed. It's that sort of messy thing that doesn't let me do all the rest of the stuff I want. But you know, we still need to use it. So we have functors on our category of monads. We have all these pointed structures. Now let's go back to the thing that I actually wrote before. So lift is the sort of canonical monad homomorphism from M to T of M. And I've got a little note here that says it's monic unless T is terminal. Yeah, this is going to be great fun to explain. So when we do, we work with sets, we start talking about functions that are one-to-one or onto or surjective or injective. We all use different vocabulary for this. Like, you know, does f of A equal f of B imply that A equals B, kind of stuff, right? When you move into category theory, you just have arrows floating around, and like the meaning of these things is a bit more abstract. So how do you like model that same kind of concept? So I want to be able to talk about injectivity, so that I know that everything that I can express in this monad expresses a distinct thing in this target monad. I don't lose any information. And I want to be able to talk about when everything that could be expressed here can be expressed in this monad, that like the image of this is the entire range of this monad. These are the two like this is the sort of injectivity, surjectivity kind of equivalent that arises in category theory. So, and the way to, oh no, let me go back to that little sort of note-taking window that I have here. If I have, say, let me just draw a little diagram pictorially. I have F. I have two objects. I have an object A, an object B, and I have two arrows. Huh? Look, there are two of them. And they go to an object C, right? We call this one F, and we'll call this one G, and this one H, right? How do you like my ASCII art? So what we're saying is something like, if G dot F is equal to H dot F, does that imply that G equals F? Okay. Or G equals H. Did I get that right? Yes, G equals H. So I want to know if I can subtract off a common prefix and use it to reason about equality. Okay. And this only really works if sort of, what is this? If F can generate every single possible B, right? If you think about this in terms of sets, right? So in the sort of, this is the one-to-one, or onto, this is surjectivity equivalent, is the ability to say that I can sort of rip off a common prefix. If I can reason that these two arrows are in composite are equal, then I can rip off a common prefix and the residue will be. Now we're going to do more ASCII art. Oop. You can guess where this diagram goes. We have G and H. It's not as exciting. F. And what we're saying here is that what? F dot G equals F dot H entails that G equals H. Okay? And what is this? If we only have access to these, then every B has to be mapped onto a distinct C. Right? This is one-to-one. We can't lose any information in this map. Here we had to be able to sort of generate everything. Here we can't lose any information. And since the category of monads over Haskell is sort of like set plus some stuff, the set-like behaviors where the sort of injectivity, surjectivity, intuitions actually hold. Okay? Now, it turns out that if you have a right inverse, that means if we're looking at F, and F has a function, let's call it G, such that F dot G is id, if there exists such a thing, right? If there exists something that you can take the input into G and then split it out into all the different equivalence classes worth of data that F wanted to process, and then make sure that everything got mapped back so you didn't lose any information. If G can kind of only put one thing in each one of the distinct places that F has that's going to produce each output, then we're automatically epic. And we call this thing a split, this is a crazy term, a split epimorphism. And I lose everyone in the room. Okay? This is sort of like, what we're looking for is a sort of right inverse to F. And it turns out that if you have, and so if you have such a thing, then you can take, let's call this R. Then G dot F equals H dot F would tell me that G dot F dot R equals H dot F dot R. I can smash these together, show that this is id, and this tells me that G equals H, right? So split epimorphism implies epimorphism. So it's a stronger condition. That we have a right inverse, that we can actually talk about it. And then you can guess what we're going to get down here. We're going to build this thing. We'll call it a split monomorphism. And this is that we'll have like L dot F is id. And this will imply the same thing because we can do the exact same trick, putting the left inverse on the left of our F and showing that it cancels and that you get the thing that you want. Okay. And then these are sort of weaker conditions than just saying that we have a monad isomorphism, which is that we have an F and an F inverse such that F dot F inverse equals, F equals id and F inverse dot F equals id, right? So a isomorphism will be both a split epimorphism and a split monomorphism, right? Because it has a left and a right inverse, which is just its inverse. They're the same thing. Okay, now I have the vocabulary that I want to use to talk about the different monad homomorphisms that we have. I haven't quite decided if it's worth trying to capture the injectivity notion. In some sense, if I'm trying to use this to sort of swizzle the parts of my state or my environment for my monad down to run my tighter computation, it would be nice to know that I don't lose any of the information that this smaller computation is using. If I want to not lose any information, then this embedding should really be an embedding. It should be a monomorphism, right? That I didn't forget anything. It's also useful to be able to talk about the rest of them. So maybe I don't want to create something, I don't know, we would call it maybe a monomorphism restriction about how we work with these particular monads. Maybe we don't want to create another one of those, but it's that's the core vocabulary we have. Okay, so now Lift says that the embedding of M into T of M is monic unless T is terminal. What the hell do I mean there? Okay, so we have a category, and in category theory we have this notion of an initial object or a terminal object. So what is the initial monad in the category of monad homomorphisms? Anybody? Identity, yes. The identity monad sort of plays the role of the one element set in set theory here. It's the, and what is return? Return is a map from sort of identity of A to M of A. We just kind of get rid of the identity because there's a real identity there, right? So return is the canonical morphism from my identity monad to my particular monad. So return, like with a run identity bolted on the front of it, is a monad homomorphism. Right, that's sort of the first one that we all know and love. Lift here is a monad homomorphism, and we have the initial object, but what's the terminal object in the category of monads? This one's a bit more of a tricky question because it's not. It's not quite. It's actually proxy. So I have in the data.proxy module, which is now in base, there's a proxy A is proxy. Yay, this is a monad. What's return? Proxy. What's bind? Yeah, it's proxy. What's, right? It's a great monad. You can do anything you want in it. It's hard to run. Well, you can run it. You don't get any of the data that you actually wanted to do, right? This monad should be an instance of like everything, right? It should be a monad IO. You can embed IO actions. Go. It's proxy. So lift IO, yes, there's a missing instance for lift IO. I have to put a patch in for that soon. It actually matters that lift IO that we have this terminal instance. I actually needed it yesterday. Okay, so proxy is our terminal object. That means that there is a unique monad homomorphism from every single monad to proxy. What is it? It's the unique map that sends everything to proxy, right? It gives you the proxy data constructor and ignores all of the structure you had before. Okay? The unique map from identity is to use return and get rid of the identity constructor. So what I'm saying here is that it's monic unless T is terminal means that every lift that you can define for every monad you can come up with you have to keep the information for identity. You have to be able to map your in this case it's for a monad transformer. So if you embed a monad into another monad using a monad transformer, right? M embeds into T of M. In order for that to work, I have to be able to produce the output A or whatever that I had. I can't forget any information through lift. So lift never forgets anything. And the only way that it can forget something is if I had a terminal monad transformer. So we can have monad transformers where we talk about the initial monad transformer. What would be the initial monad transformer? Identity T, such that the way that we map we have monad transformer homomorphisms, which map, say, for all monads M, I'll take, and objects A, I'll take SMA to TMA would be a monad transformer homomorphism between S and T, right? And so then we have identity T as our initial monad transformer. What would be the terminal monad transformer? This is a concept that has been missing in Haskell. I didn't bother to write it till now. Yes, let's make proxy T. Proxy T, MA is proxy T. We have a lovely monad transformer here. If M is a monad, proxy T is definitely a monad. Right? And it should be an instance of all the things. This really should be like an instance of like monad state for all possible S's. However, we can't be because, you know, we have the little pesky fund app. And Roman's probably laughing right now. Anyways, so we have proxy T, we have this initial and terminal monad transformer, we have an initial and terminal monad. And what I'm saying here is that lift has to be monic unless T is isomorphic to proxy T. Right? You can't use anything less than all of the result monad. Okay, so I'm trying to use this to build a little bit of familiarity with these terms, these sort of concepts. IO to ST and ST to IO, these sort of just establish that these two things are isomorphic. Yay, we have a monad isomorphism. Unsafe IO to ST, unsafe ST to IO, well, you can leave that to that's between you and your priest. Lower codensity, we have lift that can take M and embed it into codensity of M. But there's an operation that lets me take codensity of M back down to M. And it's a split epimorphism. It's surjective. We can generate every single possible M from codensity of M. Codensity of M is bigger than M. It retracts the lowering codensity sort of contracts away the like expansion that we get from lifting into this larger context. Unata and co-unata are the same size as the original thing. And these are examples that if you haven't had to use these particular monads, don't worry about it. If you have, then those lines are for you. If you use lens, there's zoom, which lets you zoom in on part of a state. You can say, if I have a lens that knows how to get a smaller state out of a larger state, I can run a computation for the smaller state directly in the larger state monad. And so if L is a lens, then zoom will be a monomorphism because we're basically able to embed something designed for a smaller state. Magnified is the same thing for environments, for reader kind of stuff. And these, I didn't bother to write the type signatures here because I don't have that much screen space. If you flip run reader T or whatever, you're going to get, given E, I'll give you reader T E M goes to M. I'll give you a monad homomorphism from reader T E of M to M. You can think of this like, almost like lowering back out of reader. You pick the environment you're going to do, and you can run. You look at eval state T, like you give me a state, eval state like discards the result state, right? We lost some information. But it turns out that I can get you any computation in M using state TSM, which isn't surprising because lift. This is sort of this undoes lift, right? In a sense, because lift can't care about the particular choice of state that we ran our state machine with, and so this has to be split epi, right? Okay, so we have what a monad homomorphism is. I already sketched that. Just because I wanted to get away with a fewer parentheses, I use this little flip fmap thing from Lens, which you can think of the less than $, greater than. This is the version that puts the function second, because the function tends to be big and long, and the thing that I'm mapping over tends to be small. And I would usually, otherwise I have to put parentheses around any particular local lambda, and now I don't. So transform, we've already established, is just, we use the lifting class instantiated at monad, right? We have our notion of pointed, which we talked about earlier. I have some existing codensity, Oneda, et cetera examples, so I can just say that we can lift those because I wanted to be able to work with them in this framework. Pointed T, oh, that's wrong. This is just lifting monad. Hopefully I didn't break everything just by changing it. I did. Okay, oh yeah, I started redefining proxy T, which I'm gonna define later. And hoist is this fmap-like operator. And I was saying before that you can't map over cont with hoist, because let's look at cont. What's cont T look like? Cont T RMA is cont T, and then we have A goes to M of R goes to M of R. Right, and then run cont T or something like that, yeah. Which is just enough to push it off the screen, making it less useful than I wanted. Okay, so with this, with cont T, how can I map, if I have a monad homomorphism from M to N, I can map over the result M and give me an N, but that doesn't help me work with the argument, because the argument's in contravariant position, so I would actually need a mapping from N to M. You need a full monad isomorphism. You need to know that M is isomorphic to N, so I can convert M into N and N into M willy-nilly in order to be able to map under cont. So I wanted to show you that cont really isn't a functor on the category of monads, like the other monad transformers that we have lying around. And almost any of the CPS monads that we like to use for like efficiency, or we codensity something, or like CPS it, but then put lots of M's in negative position, none of those will work this way. So keep that in mind. So I can make like a one-off combinator for hoisting cont, where you're supposed to prove to me that these things are two halves of an isomorphism. So maybe it would be better for me from a software engineering standpoint to like make types for capturing whether something is epi or split epi or iso or whatever, so that I can drop in, you give me an iso here, and I'll make sure that there's less lying that you can do to me without really being explicit about lying. I haven't decided yet, so I'm still playing with this. The API is entirely open for discussion, and a lot of this is really just like mfunctor and this kind of stuff is more or less the mmorph API, because I stole their names this morning, with the addition that instead of just using monad trans, I absolutely need that lifting monad thing that is the missing concept in mmorph. Okay, so each one of these things is an M functor. What's this saying? It says that if I have a monad homomorphism from M to N, I can run underneath identity T, or underneath state T, or underneath reader T. These are all boring boilerplate. We have the unique monad homomorphism from M to proxy, which I mentioned before. The lovely instance of monad IO for proxy that is missing from base. Now that monad IO is going to base, so I started playing around. What I want to be able to do is like figure out how to swizzle these inputs to get to the monad that I want. And monad transformers don't commute, right? You can't always push every monad transformer over every other monad transformer without changing definition, changing the meaning. Fine. Let's be explicit about when we're changing the meaning, and then you can use that as your way to embed this smaller action into this larger context, or even a larger action into a smaller context by providing it an environment or state or whatever you want. So this lovely thing says, give me two monad transformers, S and T, and I'll say that they commute if you can give me this morphism. And I'm not going to claim that this is an ISO, but I will say that commute.commute should be commute, right? That it's either got a left inverse or a right inverse. If you can write this, it'll then if you write the commute for S and T and for T and S, then darn it, one of them should be the inverse of the other. That at least gets me something to reason about. So turns out that we can always push, we can always pull reader T out. If I have an S of reader T, I can always get a reader T of S. Yes?
But it's not necessarily symmetric. If you have commute of ST, you don't necessarily have commute TS.
That's correct. If you have both instances, then you'll have the commute.
Right, but that's
Commute law.
Yeah.
Yes, but that law only, yes, that law is remarkably painless until you write both instances. Yes. So we can always pull reader T out. In general, there's a sort of obvious in retrospect law that says if you have M of, EA, I can always give you E to M of A. I can take the E and F map over just applying the E that I've got to the function, right? So for any functor F, or for any functor M, there's always this. So this gives me a sort of a distributive law that lets me pull readers out. And then there's a similar law. I'm going to actually make the font a little bit smaller because I wasn't just careful with the code here.
There are displays everywhere, so it's not a big problem, size.
All right, so let me look at this a little bit closer. This is a mess, isn't it? So I have S of reader T. I'll do one of these in detail so we can see it. So in order for me to be able to work with the output here, I need to know that reader TE of S of M. I need to know that S of M is a monad to talk about reader TE of S of M as a monad. So what we do is we say, hey, look, if I told you M was a monad, could you please tell me that S of M is a monad? And transform will do that. So I just case match on that. And that when I open up this sub, it's going to take my monad in. And when I pattern match on this dict, it will give me back the monad for S of M. So now I know S of M is a monad. So within this case statement, I can use that fact within the body here. So now we can say reader T, E, and here I'm going to give you something in the S of M monad, which will be, we're going to run our previous computation, which is S of a reader computation, and I need to turn my reader computation into an M computation, right? I have reader TEM, and I need to get M. Underneath S, so we have to hoist to get under S, and then we basically run reader T at the particular choice of environment, which we established earlier was epic, and we are all good. Okay. Ugh. So this works for every monad transformer and reader T. So reader T can, we only have to write one instance here. But then when you want to have reader T on the left, each one of those is going to be done pointwise. And writer T has the same kind of property that we can distribute in products. We have, if you have E comma M of A, you can always build M of E comma A by capturing the E, putting it in the environment, F mapping over this with put the pair with E. So there's a distributive law that lets me shove products in and pull functions out. Those are the kind of two distributive laws that we have available to us on Haskell. Actually, those are the only two. Everything else is equivalent. And so we have commute for writer, which is a mess. I have to use transform twice and hoist and lift, right? Yeah. But it works. We can commute reader and state. So like when we work with monad transformers, a lot of the steam that the sort of algebraic effects community gets is that certain monad transformers all commute. Like reader, writer, state, doesn't matter which order you handle those effects. The results are all the same, right? RWS exists as a monad because, yeah, like you can throw them all in a blender and they just all commute. So it doesn't matter the order you'd layer them anyways. So if I commute reader with state, it doesn't destroy or create any information. If I commute reader with writer, it doesn't create or destroy any information. Reader with accept, even. Reader commutes with accept, which is the either T that we finally got into the MTL. State commutes with writer. So state, writer, reader, we expect those all to be able to commute in all positions. Except with state is not semantics preserving. So we have the exception transformer and state. In one layering, we have a state when we fail. We have state that survives failure. In the other setting, we have the either on the inside. So let's see, what do we get? We get either S goes to either E or A comma S, or S goes to either E, A, S. These are the kind of two layerings they get for state T and either T. All right, so I'm assuming that the underlying monad is identity and using either rather than. But so these two things have slightly different semantics. Well, this one is surjective. It's onto. We can represent every computation in what? Every computation that of this form, given this form. So given one of these, I can give you one of these. And every single one of the second can be represented given the first. But when I come back, I lose some information. There's like, because when I don't have a state, because I terminated early, the only thing I can do is give you back the original state. So I lose information. And this is why, like, maybe I do want to start being careful about whether it's a monomorphism or an epimorphism. And I'm just trying to figure out if I should. Right now, I can just talk about commute, hoist, commute, shuffle things around, and pull monad transformers up and down the stack willy-nilly. And then, since you're being explicit about how you get the monad you want, you're okay. Well, it's on you. Let's put it that way.
So this is like not true commutativity, right?
Yes, this doesn't say that they. Yeah, I didn't. This does not. I did not require ISO. I just knew I wanted to commute these two things, and whether they actually, or whether the result is an isomorphism or not, is something that this may or may not stay as one class. They may split them to get the embedding projection kind of pairs. But I just wanted to sort of start getting a vocabulary for talking about how to move monad transformers over other monad transformers. And this was the sort of first thing I could think of was, let's start sliding them past each other, at least in pairs. So at least I can be explicit about when it's a split mono, split epi, right? And maybe the type should capture that, you know, because we like those. I stole, I think I was calling this like init or something like that because it's the initial morphism. We have that thing lying around. And we can always sort of, how to put this? Let's look at a good example. Here's a fun one. You can always run a reader computation inside a state. You can take the state and make it your environment, right? Reader is sort of less expressive than state, but everything, you can express everything you can express with reader with state. So this is so if I want to embed a reader computation in state, it really is a monomorphism. And it's split because there's an inverse, which is basically eval state T with a reader T bolted in. So we have like evaluate.read-only as id, and we can go back and forth between these two representations. What other fun ones do I have lying around here? If I have a writer T computation, I can always forget the thing that I was calculating, the monoid. Just forget the monoid, and that's a monad homomorphism. If you give me a starting environment, we have a way to project out a reader. And this is split epi because it has lift as its right inverse, right? There is a right inverse. There's a way to embed into this thing that this thing doesn't or preserves. So earlier I started talking about monads, and they were more of a curiosity because like what other things could I do with layers other than start flipping them? I can start smashing them together. And it turns out that Gabriel had already implemented this class in the mmorph library, so I stole his names after re-implementing it. So yeah, we got to the same point. The difference was that he used, I think, embed as the primitive definition, and because I have access to transform, I can actually either one works for me. Without transform, you can implement the other one in terms of embed really easily, but implementing embed in terms of the other needs the ability to prove that T of M is a monad given M is a monad. Ugh. So this lets me sort of squash layers. So if I have a reader T of a reader TE of a reader TE of something, which is not a situation that ever actually arises in practice, you could smash it down to a reader TE by sort of sharing E's. You can do the same thing to writers and a bunch of other stuff. Identity, maybe. You know, they're kind of obvious when you think about it. Okay. So I want to go back to the bit that I started with when I was talking about how the category of monad transformers is a monoidal category and has all this fun stuff. At the very beginning of this talk. So this was the construction that I was building to make the Poland talk go. Which is that if it's a monoidal category, there's some tensor, there's some bifunctor on the category of monad transformers that is associative and has a unit and satisfies MacLane's pentagonal coherence condition and all sorts of fun stuff. So what is that? Well, this would have to be, you give me two monad transformers and the result is a monad transformer, right? So, well, let's see, how do we do this with compose? We nest, right? Monads don't compose, but monad transformers do because the monad transformer kind of contains its distributive law of how it gets, or how, not its distributive law, but its operations of how do I build a monad out of an underlying monad. But in order for this to be a monad transformer, I need to know that T of M is a monad, which is, again, that same lifting monad concept that was missing all along. So in order for tensor to exist, I need access to lifting monad. In order for it to be a bifunctor, because it has to be a bifunctor on the category of monad transformers, I have to be able to map over this with a monad transformer homomorphism. You need to be able to give me a monad transformer homomorphism. I need to be able to turn S of T of M of A into S prime of T of M of A, given a monad transformer homomorphism from S to S prime. I need to be able to do the same thing on T. What that means I need to be able to hoist over S. So what does that mean? That you can't use Kant with this tensor. So this isn't really a tensor on the category of monad transformers. It's a category on the subcategory of monad transformers that happen to be real M functors or monad functors on the monad real functors.
Categorically defined. Can you define tensor more? Tensor more.
So okay, so you know what product does in Haskell, right? So what we're looking for is something where you have like an associative. Yeah, you need associativity. We're going to need a few operations. You need like an associativity operator, which is going to say something like, I can say A, B, C, and it should be natural and all the right things. You should be able to go back and forth between this and A, B, C. And if we have a unit, we should have something we'll call like lambda. These are terrible names, which should take and say that this is isomorphic to that. That should be row. And by the way, these are for left and right. I didn't name them. Blame the mathematicians, they like their Greek letters. So we have these things with the obvious identities that, well, a not so obvious identity involving, like if you associate twice and use one direction, if you try to associate A, B, C, D into, if you try to go from here all the way to A, B, C, D, there's two different paths you can take using a sock a couple of times in one direction and twice over here and three times over here. You know, with how you move the tuples around. That has to commute, and a couple little triangle diagrams have to commute, but they're all the obvious things, right? You need this associativity and you need a unit. And it's kind of the place that you build monoids is that, like, well, if you think about it, append, we write it as M to M to M, but this is sort of M comma M goes to M. And what's the unit for tuples? It's, well, unit, right? So mempty we write this way, but a category theorist would be happier thinking about it this way, right? So whatever the unit was for my particular tensor, I give you a morphism from that to M, and you give me one that goes from the tensor of M and M to M, and we get something interesting. So if we move to like the category of functors over Haskell, okay, we can equip that with a tensor. We're going to pick, well, these are going to be, you go from compose MM to M. And what's the unit for compose? What's the identity? I'm sorry, what's the identity? So what's this? Well, this is, if we turn this into, this is return and bind, right? This is how monads are monoids in the category of endofunctors. They're monoid objects with respect to functor composition being the tensor. Okay, so that's where the name comes from. It's inspired by that. And so we just need this. We need some ability to associate. We need some ability to put on and take off a unit, right? So let's go see those operations in this horrible format, which isn't that horrible. Oh, the instances are horrible. Let's skip those. So what's lambda? Lambda needs to be able to put on or take off an identity T, because identity T will be the unit from a tensor. So what do? We just put on or take off identity T. On the outside, it's easy. On the inside, we have to hoist, right? And then we can assoc, which, okay, that's a little dense. But what we're saying is that if you have tensor of tensor, so like you have ST, tensor ST, tensored with U, can be turned into tensor of S into tensor of TU. Right? And then the vocabulary here is unfortunately verbose, but whatever. In order to do that, I have to use that proof that M entails monad for M, monad for T of M, right? Twice. And then I can hoist and play some games, right? So yeah, it's messy. And then unassoc does the same trick. Tensor, tensor, hoist, run tensor, whoa. But all we're doing is putting on and taking off the tensor new types at the appropriate levels. So that exists. And I don't have a purpose for it yet, but it's it's coming together. So what I have is, like, we can say that if if S and T are, like, everything here should be really be an M functor or whatever. We really want to get it, so we can say that if like S and T are both monad trans, then the result is monad trans. You need real pointed on one of them. In general, lifting monad on both of them implies the whole thing lifts. We just ask GHC to do all the work. If both of these things are functors on the category of monads, the result is a functor on the category of monads because we can hoist. And yeah, that's fun. We build the functor instance by lifting the definition of fmap. We basically steal S of T of M's fmap and just use it for ourselves. And I do that overall for each of the operations point-wise individually so that they all get the optimal definition that's available. That would be available if you just composed the underlying monad transformers. So all we're doing is associating the way that we nest our monad transformer. We gained and lost no information here, right? We gained the ability to use that all of the monoidal category vocabulary for talking about this stuff, which didn't do me any good, which is why I went and did all the rest of this stuff. And then, like, in order to be able to work with the tensor of two transformers and, like, get a monad state instance for it, which is going to be, like, the way that monad state propagates out through monad transformers is peculiar to each one. We steal them directly from, well, do we have a monad state on S of T of M? Great, then we'll use that one. Monad writer, etc. And you can very easily see which effects are algebraic by if they don't include run tensor, because that's partially handling some stuff. So, which indicates that eventually I should get around to breaking the entire Haskell ecosystem and splitting apart monad reader and monad writer into 2 subclasses each, because you really want the ask part and the tell part separate from the pass and listen and the local operations that we bake into reader, because there's lots of things that can supply ask but can't supply local. But the screaming of every user of the monad transformer library is something that I'm not looking forward to, and so I've been kind of just turtling and pretending that I don't have to do this sometime. So what do we have here? So we've got those things. We've got our proxy T, right, which is monad trans. Hey, check it out. It's a functor. It's applicative. I have some wonderfully well thought out instances here. And I really want to be able to say that it's a monad state for all S, but I'm not going to remove the fund up from the MTL. And so we've got all the things. I can play with a few other ways to transform my environment. And I'm going to run a little long here, so I'm more or less running out of steam, so don't worry. Which is that, like, if you have nested readers, in many ways if you have a reader T of A, or reader T of E of something, and reader T of, a terrible letter choice, reader T of C of reader T of C of reader T of D of something, then this is equivalent to having reader T of C comma D of something. So I wanted the ability to start moving multiple states or multiple readers into one, to glom it together into one environment or one state. And so this is sort of part of my attempts to let's start trying to build a vocabulary here. I'm not fixated on this particular implementation of vocabulary. I'm fixated on the notion of having a better vocabulary for talking about these monad homomorphisms. So here, like, if T of A is a transformer, and T of B is also a transformer, then what I want is that T of AB should be I should be able to take a T of A of T of B of M and give you a T of AB M and unpair. So I should be able to tuple and untuple. And then because I want writer T to be an instance of this, writer T only works if the two things are monoids. Well, a good thing that product monoid exists. So here what we get is, if you can prove to me that A and B are both objects, then you should be able to prove to me that the pair of A and B are objects with respect to this, right? So if, in this case, for writer T, it would be like if A is a monoid and B is a monoid, then darn it, the pair of A, B better be a monoid, or we won't be able to build writer T of pair AB. And then I need some proof that if A is an object, then of T, the thing that T of A is a transformer whenever A is an object that we're willing to work with. So now I can build things like, and then lower unit lets me go through and say that writer T of unit of M is isomorphic to M, actually. So this is actually the other half of this. Is like, if I lift into writer T of unit, I should be able to smash it back down. Or if I lift into state T of unit, I should be able to lower it back down. Like, these are just things that should exist. Darn it. So I can build the instance that lets me merge neighboring states. Or I can build one that lets me merge neighboring writers. Or neighboring environments. And I thought I'd be able to do either that way, or do either T that way, but of course it's not. You actually need to use coproducts for that. So we have the sort of dual construction here, where we want to be able to take T of A of T of B of M and give you T of either AB of M, and T of either AB of M and go back. And this one works for things like except T. So you can say, either T of either T. If your nested T levels could be either T of either the two possible failure types. Yeah. So I've got these things lying around. I'm looking for better bits of vocabulary, though, for how to do these embeddings. I'm not really sure if I should package these things up the way that I have, where they're just naked monad homomorphisms, or if I should use a more lens-like trick, where what I do is I can package an ISO as a thing that you can compose with dot and then give you a combinator that lets you run the isomorphism forward or flip it all around and run it backwards. The lens-like vocabulary is not quite right, because it would be like having isos and getters, which would get you sort of monad homomorphisms and isos, but I need this whole continuum in the middle of epimorphisms and monomorphisms and split epis and all that kind of stuff, right? For which way I have an inverse, if I really want to capture that vocabulary. And I don't have the answer here. So I'm more than happy to talk to people about this if they have strong preferences or like have ideas. There's stuff that I would like to be able to do. Like I would really like to be able to sort of automatically construct the or a canonical selection of a monomorphism, if it exists, to embed. Given a list of constraints, give me the type for a monad transformer stack that implements that chain of constraints, the monad state, the monad this. So a checker that just takes an H-list style list of constraints and tries to build a monad transformer stack out of it, which turns this into an effect system. So there's some stuff that I would like to have there that I don't have yet. I haven't quite worked out the vocabulary for. And I'm happy to talk to people later on today and tomorrow about this or whenever. And I think with this slightly long rambling ending, I have covered everything I really wanted to talk about today. Thank you. Yes.
So you could open with commenting that performance was sort of one.
Yes. Performance is my goal. I don't have good benchmarks for you.
So you're moving some layers from the dictionary lookups that you're doing, but
yes.
Still the inlining problem, especially in the case of recursive functions, is still.
So what's going to happen is this: if you write to a particular concrete monad transformer, right? If you wrote to either T of state of something, right, of IO, right? Darn it. Then what's going to happen is GHC will be able to inline all those dictionary lookups to go. It's going to know exactly how to do IO here, and it'll, by the time it gets done doing case of case kind of analysis and stuff like that, like that'll turn into really tight code for this core loop of whatever it is that you wrote. Well, the goal is you don't write to the polymorphic case. You write a particular concrete computation, and you tell me the monad homomorphism that lets me embed that thing into my monad. So my goal is to sort of worker wrapper transform all of my monadic computations. Write the concrete thing that I want to do, and then write the monad homomorphism that lets me run it in the larger monad that I'm interested in. Now, I won't be able to get away with the exact existing monad transformer vocabulary because I can't just say monad state, monad whatever, and build up the bag of constraints and then have the worker convert it to that form particularly and come back. There's going to be some extra noise, but that's the gist. Yes?
Can you scribble down how you would like it to look like in practice in this specific performance critical case, like to show how the code you would like to look like?
Well, no, because I don't know yet. Like, the whole point here is I'm trying to figure out what the API should be. I have the gist of it, right? I have you can look at the mmorph documentation because Gabriel is much better than I at putting together long-winded examples about how to use this code. And that gives the gist of how you can use just the stuff that we have today. I don't know that that's the API that we want in the long run. And I don't think I can sit here and bang out a big long H-list-ish kind of sketch quickly. We can definitely talk about that one offline though. So, any other questions? All right, I think we're good. Thank you.
Thank you.